Okay, all right. I think we can start. So hello, everyone. Welcome to the second Meet the Department seminar this quarter. And today we are very happy to have Professor Peter Shearer and Matt to join us. And Peter will give the presentation first and then a short question Q&A session. And after that, Matt will give the second presentation. And after that, we will open the floor for questions. So first, let me briefly introduce Peter. Peter's study covers a broad range in geophysics. He studies earthquakes from small to large, and he studies Earth structure from the crust to the core. And Peter is most famous among graduate students for his essay, Why You Should Study Geophysics at Scripps. So welcome, Peter.
Okay, well, thank you. Thank you all for coming. I guess I had thought that I might be giving the talk in our conference room, which would have been nice, but we're still not quite there yet. But anyway, thank you for being on Zoom. Let me share my screen and go to presentation mode. I assume you can all see that. If not, say something. Okay, so we'll see if I have the right number of slides. When we have a large earthquake, like 1906 rupture you see in this famous photograph, there's a lot of information that we can gather about them. But small earthquakes, of which of course form the great majority of the ones that we record as seismologists, we just know about these from the seismograms. We don't have any direct measurements of their physical properties. So a lot of my research is focused therefore on what we can learn just from the seismograms alone. And two key parameters for earthquakes are shown here. There's the moment, which is related to the product of the fault area and the slip on a fault. And it's the most fundamental measure of the size of an earthquake. But the moment alone doesn't tell you whether you had large slip on a small fault or small slip on a large fault. And that is more related to what we call the stress drop, which is the change in the shear stress that occurs on the fault. So in order to compare our seismic observations to these models of earthquakes, we need theoretical results. So you can do these numerical simulations of ruptures, and they predict the displacement pulses you'd see in the far field. You can also compute the spectrum of those, which are shown on the right. And that then gives you a relationship between what you should observe and the source parameters. So this far field displacement pulse, so you should in theory record from these ruptures, you can relate to the moment. It's proportional to the area under the pulse. And then the pulse width that you see here, I'm just showing as tau, that's related to the physical size of the source. And as we'll see later, it's that size. If you know the size of the fault and you know the moment, then you can compute the stress drop. So if we work in the frequency domain rather than time domain, we compute the Fourier transform of this pulse, and we plot it on a log-log scale like we almost always do in source spectral studies. Then it has this flat part, that's the zero frequency amplitude that's related to the area under that pulse, but it's also proportional to the moment of the earthquake. But then we also see you have a change from the flat part of the spectrum to the part that starts falling off. And that, of course, is related inversely to the pulse width. Okay, this is kind of a complicated slide, but it's to explain then how, all of the steps we need to do to try to get at the stress drop from our source spectrum. So what we assume here in this figure is that we've somehow been able to correct for Q and anything along the path, any sort of attenuation that might also affect the shape of the spectrum. So we assume we have a true seismic source spectrum, and then we're going to fit that with a theoretical curve from which we can get the corner frequency. Then we use somebody's model. A common one is the Madariaga model, and that gives us the size of the fault. And since we don't typically know any better, we just assume the fault is circular and has a radius r. And then there's this analytical expression, once you know r and the moment, to compute the stress drop. One of the things to notice in this equation is that our r value is cubed. So if we have a small amount of uncertainty in the size of the fault, it's going to translate into a much larger amount of uncertainty in the stress drop. But this all depends upon the fact that we've been able to correct for the path effects, that we have the right theoretical model, and also that we have complete sampling of the focal sphere, we call it, because we can have radiation pattern and directivity effects that are going to need to be averaged out. Okay, but when we look at real data, things get more complicated, and this is because the seismograms we observe don't usually look like those simple pulses I showed you from the theoretical model. You also have, these sort of bumps and other irregularities. And also, I just assume that we were able to correct for Q, but often these things aren't known that well. So, an approach that I like and I've used for a number of years, we call spectral decomposition. And this is good for large data sets in which you have a lot of sources, in this case, earthquakes, and a lot of stations. And then you try to decompose the observed spectrum as a sum of these terms. I should say, this is in log space, so we're doing a sum in the log spectral space because it's a product of the spectrum, and then in time domain, of course, it's a convolution. Anyway, you can try to solve this system, and the great advantage of this approach is it's completely empirical. So you don't need to make any assumptions about the source. You don't need to make any assumptions about the Q model, and that's a big advantage. But as we'll see, it also has its limitations. So to sort of try to make a long story short, when you do the spectral decomposition, you get these source terms, but we have a problem because this is a non-unique decomposition, in that we could add a term to the source spectrum and we could subtract it from the receiver spectrum, and that's not going to change the data. So we need to constrain the results somehow. So this is just showing what I call the raw source terms that resulted from spectral decomposition, and they've been stacked and summed by the size of the events. You can see by the log amplitude. So these are the larger earthquakes in these bins, and these are the smaller earthquakes. And you can see that these don't look like the theoretical models. But the idea here is then, because there was that ambiguity in the inversion, we solve for this correction spectrum we called the ECS. So that's that red curve, and you subtract it from all of these, and then you get the solid lines here, which now agree reasonably well with the dashed lines, which show you what how the theoretical model predicts. So the idea then is that we're able to calibrate the results, I want to use that term, so that now on the right-hand side, we have what we think are the true shapes of the source spectra. So we applied this approach back in 2006 to this large-scale study of stress drops across Southern California. And you can see the lower stress drops are shown as the red and the browns, and the higher stress drops as the blues. And you can, there's a lot of scatter in the individual events, but you can also see there's some large scale patterns, and that you tend to get low stress drops in the Imperial Valley, you get higher stress drops here. So one question you might have is, if this is real, i.e. is this a real source effect, or is it some kind of an artifact? In other words, maybe we're not doing the Q corrections right. The corrections for attenuation. For example, if we had strong attenuation in the Salton Trough that we weren't correctly accounting for, that's going to tend to remove the high frequencies. And then if we were interpreting that in terms of the sources, then those events would apparently have lower stress drops. So a few years ago, Daniel Trugman, when he was a student here, he went back to this Southern California study from before, but he applied some improvements to the spectral decomposition that are shown here. The main change that he made in terms of how it affects the results is in our 2006 study, we had enforced what is called earthquake self similarity, which means that large earthquakes are just scaled up versions of small earthquakes. And in the context of stress drop studies, that means that the mean stress drop is a function of magnitude stays the same. So we weren't trying to solve for any scaling. We were just saying that there is no scaling on average. And that served to stabilize the problem, but it then did not allow for us to check whether that's true. In other words, whether you might have a change in stress drop with magnitude. And what Daniel found is that, in fact, I should explain that he didn't do this for all of Southern California like we'd done before. He wanted to focus on a few regions. That has the advantage that the path terms then are going to be similar for each of these regions. So perhaps then if there were variations in Q or attenuation, that would be taken into account. Anyway, for these 5 regions, he then found that when you allowed stress drop to scale with moment or the size of an earthquake, that in fact, although there's a lot of scatter, if you plot the median, that it would grow, in all of these regions. So that was an interesting result. But one of the things that disturbed us a little bit is if you compare the results for Landers and Hector Mine, these are not results for the main shocks. These were large earthquakes out in the Mojave Desert, magnitude 7 earthquakes, and these are the aftershocks of those earthquakes. Anyway, you see that if you that these curves are not in the same place. There's about a factor of 4 change in the median stress drop, and that would be a little bit surprising if you saw such a large change in the earthquake properties for these two events that are in reasonably similar locations, and the events themselves look kind of similar. So why would we then see this factor of 4 change? So if we compare then to what we saw in the 2006 study, we actually also had the Landers and Hector Mine sequences, and we didn't see this factor of 4 change. But this is comparing to what Daniel got, and you can see there's quite a, although there's this scatter, there's quite a large shift. And this sort of highlights that these that stress drops vary a lot. There's a lot of scatter, even if you plot on a log scale like this. So we typically see scatter in the individual event stress drop estimates of about 2 orders of magnitude. But more seriously, if you compare studies, they don't always agree that well. So I started working with Rachel Abercrombie a number of years ago, and we would do these sorts of comparisons where we're looking at the same earthquakes and comparing the corner frequency estimates that that I got with the ones that she got, and there's just a huge amount of scatter here. So that motivated us to try to examine this question in more detail and to try to understand all of the steps that were involved in the processing, so we could see where this scatter is coming from. So we examined a small region where there were a lot of earthquakes. This is a cluster of aftershocks of Landers in this cube of 6 kilometers side. You can see these are all small events about magnitude 1 to 3. And then we did spectral decomposition and played around with the fits. And what we found is that it's actually not very well constrained, because when you allow to change the ECS function shown in green, but you also allow the scaling to change. In other words, you allow the stress drop to change systematically as a function of the event size, that there's a lot of models that will give reasonable fits, as you can see here. Here you have a non-self-similar fit, a self-similar fit. You also have ones where you've enforced, where you have a lower stress drop, and ones where you force there to be a higher stress drop. So there's essentially, it's not well posed to try to solve for what the absolute shape of the spectra are. I should say, however, once you have decided on the green curve and you use that for the processing, you're still going to do reasonably well in resolving the relative changes in stress drop within the same cluster. Okay, well, how to solve this problem. The approach that we decided to try is to drop the idea of just allowing all things to float. So here we decided, okay, for the smallest earthquakes, we're just going to assume a source model. And in particular, for the magnitude 1.5 earthquakes, we're going to assume that they have 30 hertz corner frequency. And that essentially forces those smallest earthquakes to have the same stress drop when you compute them with a theoretical model. But the advantage of doing that is if you then see differences in the larger earthquakes, that because we force the small ones all to be the same, if we see these differences in larger earthquakes, and that has to be a real source effect and not a path effect. Very quickly, why did we choose 30 hertz at magnitude 1.5? Goes back to data from the Cajon Pass borehole, which was collected during the 1990s. And this was a deep borehole at 2.5 kilometers depth into granite. So it was below most of the near surface layers that cause attenuation. So you get a relatively unbiased view of what things are in the absence of attenuation. There is a lot of scatter, but 30 hertz seemed a reasonable value to use. Okay, so the way this works then is for each event that you want to compute the source spectrum for, this is from the spectral decomposition, you see this black curve, you then search for small events that are nearby. We look for ones within 5 kilometers horizontally, 2 kilometers in depth. Those are shown here. We say, okay, we know what their shape should be, shown as these red curves. So we're going to then compute our ECS function, shown as green, is just the difference between those. And then we subtract that black curve to get the red curve, which is our new source term then that's been corrected for Q. And if we then apply this to Southern California, this is new results now, and I'm showing a map just for magnitude larger than 2 events. And all of these have at least 10 smaller events that are nearby that provide the calibration. We can see that we are now, we see red again in the Salton Trough and blue here. This is what we saw before, but we can now have more confidence that it's real because everything is plotted relative to the behavior of the magnitude 1.5 events. So any Q differences or propagation path differences have been removed. We do now, because we can also examine this scaling issue. You can see that that constraint of 30 hertz at magnitude 1.5 results in about a 10 megapascal stress drop for the smallest events. But then as you get above magnitude 3 or so, the stress drop grows. But I would say that we don't think that this is real. One of the reasons is that if you continue this up, you're going to get to quite high stress drops that are higher for these larger earthquakes than are thought to be the case. And we have more observational constraints for those large earthquakes. So we think this is a result of assuming the Brune model, which has a high frequency fall off rate of 2. If you allow the high frequency fall off rate to be shallower, then you can explain the data without the stress drop increase. Okay, so to sort of sum up, I think the fundamental observation is that for these small earthquakes, the amount of earthquake high frequency radiation we see varies. And color scheme I'm using, blue, is for higher stress drop, but it's also for more high frequency radiation, whereas red is more like a red spectrum with less high frequency radiation. And these are real spatial differences. I think a very important question that we still don't know the answer to is why do you see these variations? This could be due to stress drop. It also, in fact, could be due to the speed of the ruptures, because that also goes into the theoretical model. So you could preserve more constant stress drop if you allowed, for example, to have slower rupture speeds in the Salton trough, or it could just reflect on the complexity in the ruptures that aren't accounted for in the theoretical model. There's sort of two main ideas that could be driving this. It could be that the rock is, or the faults aren't the same. If that was the case, then when you have a large earthquake that is going to change the stress state of the crust, you would still expect to see the same thing. Or it could be somehow in response to the local stress state, in which case these high and low stress drop regions might change. One clue is that Bettina Allman, when she was here, did a study looking at both before and after the Parkfield earthquake, the magnitude 6 at Parkfield, and it seemed like the regions of higher stress drop that you saw prior to the Parkfield magnitude 6 were still there following it. So that observation would favor the first of these. Okay, so this is my last slide. And basically, I think I want to say that we can reduce the uncertainties if we fix the behavior of the small earthquakes. But I think that the ultimate goal, and I think one that will better connect our observations to real models, is to not allow things to just float purely. In other words, we need to solve for Q models and include those as part of the inversion. So I'll stop there, and I'd be happy to take any questions if there's time.
Thank you, Peter. So we'll have time for one or two quick questions.
I have a question for Peter.
Yes.
Can you hear me?
Yes.
Yes.
Great. So I didn't quite understand what the green curve is, the EGF or ECF. Can you explain it in greater detail?
Okay, let me go back to sharing my screen again. And I want to go to this slide here. Okay, so what we get from this, the result of this is, so we get a bunch of these source terms. So these are shown on the left, and they aren't what we want. Clearly, we want something that's more what we see on the right, where we have a flat part of the spectrum at long periods, and then we have a fall off at high frequencies. So the idea is we want to solve for this red curve here, so that when we subtract it from the raw source terms, we get ones that now look like the true source spectra. And we know, as I said before, we have this inversion has ambiguity in that, we can add something or subtract something from the source term, and we could then add it to the receiver term or this travel time dependent term. So since we have, all these degrees of freedom, then we're free to make we can subtract some curve from this to make it more like what we want. And we can say, okay, well then, that is just going to be added to these terms. I guess what I was sort of trying to say at the end is that isn't that good, because we haven't checked to make sure that when we've added that to these other terms, that it actually makes sense in terms of what you should get for the receiver response and the Q model. Anyway, did that answer your question?
So yeah, in other words, the ECS is completely empirical. It doesn't really have a physical meaning or something.
Right. Yes, exactly.
Okay. And then how do you empirically estimate it? You somehow did an average from the raw source terms?
Right. So you can see here, for example, how this works. If, for example, you sort of think of the red curve as a sum of the misfits between the solid lines, which are the data, and the dashed lines, which are the model. So if at some frequency, the solid lines were all larger than the dashed lines, then we would know that we would be able to improve the fit, by changing the red curve. So in other words, this red curve is what you need in order to make the average residual between the solid and dashed lines 0.
And the ECS is the same for all sources. It doesn't vary between sources.
Okay. Yes. Yeah. So there's just one of these functions, and then once you've computed it, you use that, and you go back to this equation, and then you subtract that from this term, and then you have what you think are the true source spectra at that point.
Gotcha. And also, I guess the conclusion of your talk is that you probably should avoid using such, arbitrary empirical term, but rather rely on some, more physically based the corrections or something.
Yeah, I think the problem is that you can, if you, this function controls the amount of high frequencies in the source. So if you move this up, then that's going to remove high frequencies from the source. It's going to shift all of the corner frequencies down, and you're going to get lower stress drops. And if you move this down, you're going to get higher stress drops. And that is going to trade off with the Q structure. Now, the problem wouldn't be as hard if it wasn't for the fact that most of the effects of Q are in the shallow layers. So you don't have a strong range dependence of T star or the attenuation terms. So you can make strong attenuation in the near surface layer, and that's going to trade off with all of the stress drops. You're going to shift all the stress drops higher or lower, and that kind of trades off with the Q in that near surface layer. And even though you can fool yourself and saying, okay, I improved my variance reduction from 65% to 66% or something. And you can think, that you've resolved it, but the changes in the data fit, are so small that you really, I would say that all of these models, all 5 of those models, are about the same in terms of the quality of the fit, even though the misfit functions might lead you to conclude that you've resolved something. I think you're just fooling yourself that it's really resolved.
Thanks.
Okay, so I think we will move on to Matt's talk, and there's one question in the chat for Peter, so you can take a look of it, and we will answer it in the end of the seminar. So Matt Dzieciuch received his bachelor and PhD degree in electrical engineering from University of Michigan, and then joined Scripps since 1991. He has carried out research in a number of areas involving ocean acoustic tomography and signal processing. He develops methods to monitor ocean temperatures and currents on the scales that are important for understanding climate change. So today he will talk to us on acoustic thermometry in Arctic. So welcome, Matt.
Thank you. Hope you can all hear me and see my slide. Maybe you can wave or something if you can.
Yes.
Okay. So yeah, thanks for letting me talk to you all today. And I wanted to talk about an experiment we did recently. And so I'll talk about that, and I'll talk about some of the adventure, and also talk about some of the results that we're getting. So first of all, this is a picture, my title slide here is a picture of us putting in a sound source in the Arctic. And I wanted to also say that this experiment wasn't just me. There was a lot of other people involved, specifically Peter Worcester. Many of you know Peter here at Scripps. And we had a partner, Hanna Sagen in Norway, who was a tremendous help because she was basically responsible for the other half of the experiment, which I'm going to explain in a minute. So the motivation behind this experiment, just something that everyone here knows, is that the Arctic is changing rapidly. On the right, you see a picture of the ice cover that was derived from satellite measurements in September 1984 versus September 2019. And over that time period, the amount of ice cover has dramatically decreased, and especially the multi-year ice, which is shown in sort of the white, the brightest color. It's really decreased. Now ice kind of lasts maybe a year or two, and then it disappears, whereas in the past it tended to stick around for several years before it would be ejected from the Arctic and through the Fram Strait. That's a different story, but this is what's motivating us. And the panel on the left just shows how fast it's warming. It's warming faster in the Arctic than almost anywhere else. It's warming about 3 times faster than other places on the planet. So that was what makes the Arctic so interesting. And what we were also motivated because there was an experiment done 25 years ago. And we wanted to repeat that experiment, thinking that the changes would be, there would be large changes. So this experiment 25 years ago was, maybe you can see my cursor, my mouse. There was an ice camp labeled here, Camp Turpan, where they lowered the sound source jointly with the Russians. That was when we were friendly. And we listened. Another camp was set up here on the other side of the Arctic near Alaska. And they listened to the sound that was generated from the Camp Turpan all the way across here at Simi. And everyone, I think, knows this, that it's a simple thing. The travel time of the sound is related to temperature because of the sound speed. is a function of temperature. So I have listed on here a bunch of other things that also may be changing due to the, the structure of the Arctic may be changing a little bit, specifically the upper layers, which will affect the sound. Also, because the ice is getting thinner, is probably less rough, which means that it's a better reflector of sound. And so the actual propagate the transmission level, transmission loss will be not as great now versus in the past. So those are our motivations. And let me tell you a little bit about our experiment, or about our equipment, because this is what, I mean, many of you see us, our group working down in our lab, and this is what they're doing. They're building this kind of equipment that goes out on these moorings, and the mooring is shown on this diagram here on the right. And what we do is we put these out in the deep ocean where there'll be an anchor near the bottom and a float near the surface. And then we'll have a sound source. This is not really this exact scale, it's just an engineering drawing, but you'll have a sound source. And in this case, it was 60 meters below the surface. And then we had about 1,200 meters of cable that was instrumented with hydrophones. So you can go up and buy a hydrophone anywhere, but what we do in our lab is build the data acquisition system and the clock and a means to navigate the mooring, which means keep track of where it is exactly in space. So that is something that we have, you can't just go buy that equipment. That's what we're busy building, is that kind of thing. And I have some specs listed here about the signal that we transmit. It's a sped spectrum signal, and so it's it's a way to get the if you were a signal processor, you would know that this is. But I'm just gonna. It's a phase coded signal that allows you to, because the code allows you to compress all the energy back into a pulse, and you can get a huge amount of gain from that. And in this experiment, I think we get about, I can't remember the number. I think it's 40. We have it set up to get about almost 50 dB of gain. And that was what really lets you hear a sound from one end of the Arctic to the other, because by the time it gets to the other end of the Arctic, it's much below the noise level. Okay, so now so we deployed these sound sources. Here's where we deployed everything. Okay, so in the Beaufort Sea, we had 2 listening moorings with 40 hydrophones apiece. Then we had another mooring here, the furthest north mooring, and that was about 80 north, and that had the sound source on it, the drawing I just showed you, still with another 40 hydrophones. And then that was all deployed from the Coast Guard cutter Healy. And then Hanesagen from Norway deployed the other 3 moorings on the other side of the Arctic from a Norwegian Coast Guard cutter called the KV Svalbard. And there was a second sound source here in the yellow. Both these yellow markings indicate sound sources. And so they were able to transmit back and forth. The moorings the ends are in the same locations, more or less, as the Turpan and the Simi ice camps. And the idea was to get it's important to note that, I guess, that the measurements 25 years ago were done at 19 hertz, and our sound source was not quite that low, as 25 or 35 hertz. And that affects our ability, when it gets to higher frequency, as the frequency goes up, the loss gets bigger. So we were not quite sure we would actually hear the sound source all the way across the Arctic, but in the end, it turns out we did. I'll show you in a second. And but that's kind of one of the reasons why we stretched the moorings out this way, was so that we could guarantee that we hear something all the way across, even if we had to string it together. So this is a little bit about the adventure that we had. Everything went in okay, but then pulling things out, we had a little bit of a difficulty. We went, the Norwegians went first. They pulled the moorings out with the KV Svalbard. And then we went up we tried to go on Healy, but we ran into a problem. This picture in the middle is a picture of the motor in the Healy, and it actually the coils, or whatever you call them, the copper melted, and that's white area started arcing and melted. So it's this huge motor. It's encased in this container here, and it had to be removed from the ship to get fixed. So this is them fixing it. But the upshot is that we could not use the Healy to recover our moorings. So we ended up, we were very lucky. The ONR that's our funding agency, had invested a lot. So they called up the Norwegian Coast Guard and said, hey, can you send out the KV Svalbard again and help us pick up these moorings on our side of the Arctic? And they did. So we left last October and went on this long path all the way to get the moorings back. And it took us about 2 months to get there and back. So it's also interesting to see how you get a mooring back in the ice. So this is a picture of the KV Svalbard from a drone showing you operation. And first we spend a few hours, 2 or 3 hours, cutting up the ice. And this was in August, and it was a little bit, by the time we got there in October, it was a little bit thicker and darker, so you couldn't get a picture like this. But you cut up the ice with the ship, and then wait as the wind pushes the hole over where you think the mooring is. And then if you get it done in the correct place, if you get everything done correctly, you can flush the hole out a little bit more, and hopefully the mooring will pop up in the right place. In a second here, you'll see it. And amazingly, it worked, and it worked 5 out of the 6 times. On the 6th try, on the last one, we ran into a little bit of a problem. It came up outside the hole. So we had to actually, the Norwegian Coast Guard was able to dig a hole, and I don't know if you can hear them. This was, can you hear all the video? Yeah. Oops, it looks like it stopped. I don't know what happened. So anyway, they were able to dig a hole and send down a diver and pull the mooring out of the water. So that was quite an adventure. Okay, so I have about 10 minutes left. So now I can tell you a little bit, not about the adventure, but about the data that we got back. So we got data back, and all the moorings worked. And so we were, now we're in the process of sort of evaluating what worked, or rather analyzing everything. And it's a bit like, it's not unlike, I guess, the Webb telescope that we've heard about recently, right? You have to apply a lot of corrections before you can get data out that make sense. So that's where we are now. So, but before I describe that, I want to describe a little bit about what we're going to measure. And shown here is, I'm just going to mostly talk about moorings SIO1 to SIO3, which is this mooring, this transmitter, to this one over here in the Beaufort Sea. Okay, and because it's easier to understand. And what we hope to measure is shown in the upper panel on the right, and it is the arrival pattern of acoustic energy as a function of time and depth, as measured on this array of hydrophones that we put in the water. And this picture is constructed out of acoustic modes. So the modes are standing waves in the vertical, but they propagate horizontally with a particular wave number, a horizontal wave number. And on the middle 2 panels, it shows how the travel time, which is related to group speed of the mode, varies with frequency, and how the phase speed or arrival angle varies with frequency. Okay, so when you put these two together, it's you get something called, well, you get an arrival angle versus travel time plot. And all these curves lie on top of one another, because things that travel with similar horizontal wave number, with the same horizontal wave number, will have a particular travel time. And so all of mode 1 is contained in all these little red, or I'm sorry, blue dots right here. And then mode 2 is here, mode 3 is here, and all the other things here, until you finally get to a place where there's an interference pattern and they become arrays. So those are these time fronts that you see at this end. On the left, I have a picture of what the first few acoustic modes look like. So mode 1 in this pattern is the blue here, and then mode 2 is the red one, and so forth. Now these things are, I computed all this for a very simple profile. This is a climatological profile. It's very smooth. Okay, so this is the sound speed as a function of depth. And these modes, the reason why we're interested in these modes is that they are sensitive to the sound speeds or the temperature at particular depths. So at these little dots, I have plotted the turning point, or the place where the mode changes from being oscillating to decaying or evanescent mode. And that's where it's most sensitive to the sound speed changes in the water column. And you can see they're at a bunch of different depths. So that's what we will get depth resolution out of our data. And just to elaborate a little bit more about that, and a little bit more about the climate up there, in the Beaufort Sea, there is a situation where we have deep in the bottom, we have this deep Arctic water, which is cold and sort of reasonably salty. And then above it, we have warmer water that comes all the way from the Atlantic that is actually warmer, but it's saltier. So the salt, because it's saltier, it's just a little bit warmer. And normally you'd think if it was warm, it should be way up on top, but because it's saltier, it's at this depth here. And above that, this Pacific water, which comes in from the Bering Strait, first it comes in over the Bering Strait. It's warmer because it comes in the summer, and it cools off and it sinks a little bit. Okay, and also in this upper layer is also a mix of there's a lot of runoff. Well, there's many large rivers that dump fresh water onto the very surface of the Arctic. So there's a lot of fresh water right near the surface of the Arctic. Anyway, these layers separate out into these what people call water masses. And the acoustic modes are here plotted on the right. So you can see this is why we're interested in measuring these modes, because hopefully it's going to let us take, through the magic powers of an inverse problem, take apart this structure and take a look at these different water masses. So, now I wanted to show you, I guess, what we actually got from this experiment, or what we actually measured. So after doing these corrections for the clocks and for the mooring motion and whatnot, we have the measured signal on the top and the expected one on the bottom, constructed using this very simple smooth profile that I showed before. And you can see they kind of more or less line up. And all that instrumentation that we're building is what allows us to actually put a scale on this travel time axis and on this transmission loss axis, right? Or the color scale. We can, if you just had a hydrophone, you put it out, you measure this thing, but you don't really have this aligned or registered properly. But our instrumentation allows us to keep this, to make detailed comparisons between the upper panel and the lower panel, even in terms of both travel time, where it's located, and the actual transmission loss, or the amount of energy that is gets from one end to the other. So what's interesting in this panel is that you see, I think, hopefully pretty clearly, for instance, here's a mode 3. So you see three lobes of energy, and you can see the same thing in the measured data, and it's pretty scattered. You can see mode 1 here, and then it turns out mode 2 is behind mode 1. It's not over here where we might have expected, and the reason it's not where I really was thinking it was going to be was, it is that the profile I used is not necessarily to generate the bottom plot, was not particularly accurately reflecting what the conditions are in the Arctic. And I'll show something else in a second about that. But you can see the other modes, mode 4 in here, it's hard to pick out a 5 or 6, but then you can start to see the arrival patterns or the ray-like arrivals coming in also at the earliest times. Okay, so why doesn't that line up, or why is mode 2 sort of shifted away from its expected place? The middle panel shows the sound speed profile I use to generate those patterns, the model patterns, but here's a bunch of measured ones. So it's quite different. You see, I put the vertical scales should be the same on all these things. So you see these modes are sampling this upper part of this water column, and it's the profiles are actually quite different in reality from what I used in that model. Okay. The next thing to do is to try to, I presented this picture here about the travel time versus angle. So we can actually pull that out of this measured time front plot, and we do that with this means of a turning point filter. And it's just a way of separating out things that have a common horizontal wave number, really. So I think in seismology, you do this a lot, probably with arrays. You measure things that have a common horizontal wave number. And you could, I actually have it labeled as arrival angle on this picture, because that's kind of what we're used to. We're used to looking at these ray paths and they kind of have a constant arrival angle, but you can think of this as horizontal wave number, or you can think of it as phase speed, mode phase speed. And the delay time is the mode group speed. So the here you can, it's hard to see maybe, but this is actually a movie. We can look at the how this varies over the course of a year. We left this array out for a year, and you can see mode 2 is here. Mode 1, unfortunately the color scale was chosen badly, so you don't see the actual peak, but there's a peak in here. And then mode 3 is stretched across this area. Mode 4 and 5 maybe we'll pick out here, but then things turn into rays at this end. And there's still some splitting of these rays and apparent in this picture. And that's not because the rays are actually splitting. It's because I have badly focused our Webb telescope, right? I haven't quite applied all the mooring motion corrections properly yet. So just like they're tuning up their telescope, we're still tuning up our array to get this focusing done properly. Okay, but if you pull out peaks from that diagram, you get this histogram of, or rather just collection of peaks. And this is what we'll use to try to sort out and do the inverse problem to sort out those different, look at for the changes in the Arctic water masses over the course of the year. So I'm running out of time. I guess the final thing to say is that here's mode 1, here's mode 2, and we can see them in the you can actually make a time series over the year. Oops. Didn't mean to press that. And then mode 2 is here. Some of the array paths are here. Mode 3 is quite a bit, very scattered. So we'll have to sort out how to use that. I just wanted to mention briefly that we did actually hear sound all the way across the Arctic, but we haven't quite analyzed this path, the complete path completely, or in as much detail yet. Finally, since this was a Meet the Department seminar, I wanted to let everyone know, like some of the other people that are in our department that are working with us that you see down in the lab. So I have pictures here of people that many of you have probably seen, you might not know. Matt Norberg does a lot of our mechanical work. Carol Brown, electrical work. Lloyd Green was our longtime electrical engineer, now retired. And Dave Horrow was our longtime programmer. And Karen Scott helps us take care of all the contracts and keeping track of all the grants and everything. And Dave Jabson, I don't have a picture of yet because he just joined us, and he's going to be taking over some of the work that Dave Horwitz did. So thank you very much for listening, and I'm happy to answer any questions.
Thanks, Matt, for the wonderful talk. Tianze, questions?
Thanks. I'm a little bit unsure about your observation geometry. Did you put the source on the same cable or the vertical cable with your receivers?
Yes.
And
Yeah.
but the receiver is for listening to the source on the other end of the Arctic Ocean, not for the one right below it.
Right, right. So we put a source here and right, and then we put hydrophones here. But these hydrophones, they do listen to the actual same sound source on the mooring, but it's only just for calibrating the source. But their main purpose is to listen to the sound source on the other side of the Arctic, right? And
I see.
And then the moorings that don't have sources, it's just this is just this piece is not there. That everything else is, all the other hydrophones and controllers and things are all there still. Yeah.
Thanks. I guess I have another question. So what is the main propagation depth of the waves generated by the sources? So it's not in the SOFAR channel, right? Because they are kind of more on the shallower layer of the Arctic Sea.
Well, in the Arctic, I'm going to go back to my screen again. In the Arctic, it's not like the, here we go. It's not like the temperate ocean because the profile, the profile looks like this, and the sound channel axis is near the surface. It's not, in the temperate ocean, it would be down around 1,000 meters or 1,200 meters. Here it is, the water is mostly the same temperature, right? The temperature plot that I showed you, it has a very narrow range, -1.5 to -1.5 degrees. Whereas if you were in the middle of the Atlantic somewhere, the surface layers in the Gulf Stream might be, I don't know, as warm as 20 degrees C or something, right? So that makes things much warmer. And that warm surface makes the water much faster. So in the temperate ocean, you have the sound channel axis doesn't form. The structure is that it's much deeper than in the Arctic. Does that answer? So the sound is mostly trapped in these upper layers in the Arctic.
Gotcha. Thank you.
Yeah.
Are there other questions for Matt? So if there are no more questions, I would like to thank Peter and Matt again for sharing your research with all the faculties and graduate students in the department. Thank you. And last week will be the last seminar of this quarter, and we hope to see you again.
Okay. Thank you.
Thank you all for coming.
Thank you.